This lesson's about resistance and Ohm's law. Here are your objectives. Let's think to our water analogy. If we have a pipe of water and we raise one end, then water that is already in the pipe is going to flow out of the end. And similarly, if we have a wire and we increase the potential difference across the wire, that's analogous to tipping up the end of the pipe. And the more we increase the potential difference, the more we will get flow of charge or current through the wire. So again, increasing the potential difference increases the flow of charge, what we call the current. The current is also determined by the resistance offered by the pipe or the wire. If you were to have a thinner pipe or a longer pipe, or if you were to put stones in the pipe, then that would slow down the flow. In the same way, increasing the resistance in the wire will decrease the current. So let's talk more about resistance. We define resistance as the ratio of the potential difference across a component to the current through that component. So let's consider, for example, a resistor like this. We talk about the potential difference across because remember that potential difference is a difference between 2 points. We always need 2 points. So here's my voltmeter connected across that resistor, and if we measure the potential difference from, let's call this A to B, we would call that the potential difference across the resistor. The current goes through the resistor. So resistance is defined as the ratio of potential difference across to current through a piece of material. In other words, R, our symbol for resistance, is equal to delta V over I. Just to note that I'm using delta V here, and I'll use it elsewhere, to emphasize that it's a potential difference that we're measuring between 2 points. But you will also see it written just as plain V on its own, and that's acceptable as well. And you can see from this equation that the units of resistance should be volts over amperes, and we give that a special name. We call that the ohm. So the units of resistance are ohms, which get this symbol, and 1 ohm is equal to 1 volt per ampere. There's also an empirical observation that gets called Ohm's law, even though it's not really a law, it's just an observation. To understand Ohm's law, let's imagine that we increase the potential difference across something and watch what happens to the current. I'm just going to use V here instead of delta V so that we practice seeing that as well. For some materials, like metals at a constant temperature, the value of the resistance is going to hold for different values of the potential difference across and the current through. So let's imagine that we have our material here. I'm going to draw it as a resistor, and I'm going to increase the potential difference across it, and I'm going to measure the current through it. So as I increase the potential difference across it, I'm moving to the right on the graph. Now, for some materials, the ratio of V over I, in other words R, is going to be the same throughout. What that would look like is something like this. Because remember from your equation of a straight line, y is equal to mx plus b, that if b is equal to 0, because the y-intercept is 0 here, then m is equal to y over x, or in this case, actually, it's more interesting to look at 1 over m is equal to x over y, because x is equal to v, and y is equal to I, and so 1 over m is equal to our resistance. 1 over the slope is our resistance. So in here, we see the slope is constant, and therefore the resistance is constant. To find the resistance at any point, we would just take the x value of that point and divide it by the y value. And that's going to be the same everywhere because the slope of the line is constant. If I want to find it over here, I do the same thing. Now, here's an example with lower resistance. This has lower resistance, and this has higher resistance. This has a changing resistance, because if I were to calculate V over I here, the x value divided by the y value, and if I were to calculate it here, I would get different values. Now, in both cases, just taking the x value and dividing by the y value is going to give me the correct resistance, but that resistance is going to be different at this point and at this point. So that's a way of thinking about these I versus V graphs. Be careful that it's not actually the slope that's giving you the resistance. It's the ratio of the x to the y value, but when you have a straight line, that turns out to be the slope. Now, materials where we have constant resistance, which show up as straight lines on graphs like this, are called ohmic materials. For non-ohmic materials, the ratio of V over I varies. So these two straight lines are showing us ohmic behavior, whereas this curved graph is showing us non-ohmic behavior. And an example of this latter is like the filament in a light bulb, where as it heats up, the filament itself provides more resistance to the flow of electrons, and so you need more of a potential difference across it to increase the current, and so it curves like this. So these are ohmic materials, the straight lines, and then this curved one is a non-ohmic material. So that's an introduction to resistance and Ohm's law.